Right, good morning everybody. Let's begin our today's lecture with a brief recap as to what we did last time. If you remember, we began looking into the problem of behavior programming. Behavior programming. And, well, all of this is done from a rather abstract or elevated point of view, so we are not actually really going to write down programs that would realize behavior for computer game agents. However, what we're doing right now is studying general techniques that would allow us to model the behavior of a game agent. And so, well, one of the questions we addressed was like, what is behavior after all? And, well, yeah, it's not so straightforward. I mean, behavior is one of these things which we recognize when we see it. It is obvious, like something behaves. But actually defining it, what is it to behave, is not that precise or easy. And we agreed that we could think of behavior as the response of a system to either internal or external inputs or stimuli. And of course, the kind of systems we are interested in this lecture are game agents. So from now on, this is a fairly general definition is such a brutal term in this context. This is a fairly general definition as to what behavior is. It involves the term system. Everything can behave. Biological entities can behave, but also artificial entities. I don't know, an atomic power plant shows certain behavior if, I don't know, certain temperatures go up or down, whatever. So there are responses to internal or external stimuli, but the kind of systems we are interested in are, of course, game agents. Now then, having encountered this term agent, which is again, you recognize them when you see them, but what defines an agent? We spent quite some time on the problem of characterizing what makes an agent, and it appears that as of today the best way of characterizing these agents is in terms of these diagrams, and we had a look at lots of diagrams that would characterize the behavior of an agent with respect to an environment the agent acts in, but also with respect to internal states of that agent. And we have looked at these diagrams you'd find frequently in the literature or in textbooks, and I poked fun at these diagrams because they're beautiful to write down or beautiful to invent or conceptualize, but in the end they are just diagrams and they don't really tell us anything as to how an artificial or natural agent actually behaves. And one of the reasons for that, like one of the underlying difficulties, can indeed be related to what we discussed at the very beginning of this lecture series when we talked about, you remember, Gödel and Cantor, Gödel, Church and Turing, when we saw that there are things we cannot count, things we cannot prove, things we cannot compute. So whenever our brain thinks about what it is that makes intelligence, what it is that creates behavior, we actually, who knows, might be dealing with a situation where we are thinking about something that we cannot really fathom because our brain is part of this system it is trying to think about and might not actually come up with an answer. So nobody knows. It's very difficult to define behavior. It's very difficult to define what it is that is an agent. And one of the difficulties in this context was this hierarchy of behavior. So we also had a brief look into that hierarchy. And that was basically to say that, at least with respect to the context of computer games, modern video games, we can distinguish certain classes of behavior. But first of all, and on the lowest level of this hierarchy, there are these reactive behaviors. We discussed that these are actions or sequences of activities a system shows just based on the current state of the system and the environment. There is not much reasoning going on here. If, I don't know, example from daily life, a fly is flying towards your eye, you are closing your eyes immediately without even thinking about it. Right? If you stumble, you probably put out your hands to catch your fall. There are things you do not need to think about. You're sort of like, the system that is you acts reactively. In a computer game, for instance, if you are a character under fire, you might immediately seek for cover or fire back without actually really thinking about it, right? And then there are these tactical behaviors which are more complex than mere reactive behaviors. These are behaviors where, again, there is a narrow scope, a certain temporal context. You have a certain goal in mind as a player. You want to achieve that goal. And in order to achieve that goal, you probably have to solve a subtask, which requires some sequencing, some planning of activities, and some degree of reasoning, because there might be obstacles, something that stands against your current sub-goal, and you have to think about what to do in order, even though there is an adversary trying to prevent you from reaching your goal, what to do to reach your goal. So there is some reasoning going on here. And of course that can be taken yet a step further towards the level of strategic behavior. When we are talking about strategic behavior, we are, thinking about the overall picture. There is typically an overall goal when you are playing, and usually you want to win the game. Right? And that requires certain things of you, maybe a lot of different things, and you sort of have to schedule them. First you have to do this, then you have to do that, or there are certain other things you have to keep in mind constantly while playing the game. And that requires you to devise strategies, like as to what to do over the course of a game. And even if while following a strategy, some sub-goals within that strategy might not be possible, and you have to, sort of think about a new tactic, or there might be something that requires immediate action. There's always something in the back of your mind as the acting agent. And you have to think about like how to realize that. Now, why would we call this a hierarchy? Well, of course we can say these kind of things are easy to do. This requires a certain degree of reasoning and planning, and this may require quite a lot of reasoning and planning and scheduling and whatsoever. So we can basically say that, let me see if this pen, so there's an arrow here, and along this arrow we can say that it requires more contextual or world knowledge, well, to even behave tactically or to behave strategically. You need to know a lot about what is going on right now, what was happening, I don't know, like a couple of seconds ago, and what is likely to happen in a couple of seconds from now. And then even, you know, you need probably to know a lot about the world. Well, you know, I am observing an opponent entering this room over there, and there is no exit, you know that. So the opponent will have to come through that door again, and maybe you just wait here to get the kill, whatever. You need to know about the world and what is currently going on in order to achieve these kinds of behaviors. And that is to say, the amount of information required to realize such behavior will grow. So in order to just merely react, it does not have to be that much information. It's just a fly is flying towards my eye, or I'm being shot at. This is, you know, very simple amounts of information. These kind of things require more information. And I already mentioned it, the higher we ascend in this hierarchy, we'll need more reasoning or planning, which are formidable problems in their own right. We'll see how much time there's left towards the end of the lecture series if we can look into that more closely. These are very difficult problems from the point of view of computational intelligence. And of course, I don't know, the more knowledge processing and information processing there's going on, the more time it will take to actually realize these things. So also the computation time, say, will go up from the level of reactive behaviors over the level of tactical behaviors towards the strategic behaviors. Now, yeah, we can talk about the difficulties of realizing these higher level kinds of behaviors, and we'll postpone approaches towards realizing these kind of behaviors. What we then did last time, we began looking into the question as to how we can realize reactive behaviors. That is, last time we began looking into the problem of reactive behavior programming. And yeah, without further ado, I just gave it away. There is a very popular and rather traditional way as to how that is done in video games, even to this day. This idea goes back to the earliest video games ever. Pac-Man, I guess, was the first where this was done formally in terms of, and that is what we began talking about last time, finite state machines. Now let me erase that. So I said that the traditional, and by traditional I really mean traditional, so this goes back at least to the very early years of video games and computer games. So the traditional, and to this day extremely popular, it's still in use, popular baseline for reactive behavior programming, or for at least modeling reactive behaviors on a computer, and thus, you know, come up with implementations, consists in finite state machines, and scripts. Okay, and we began looking into finite state machines, and we'll continue our study from this point on today. And last time we began with the example and then moved on to the definition, and today we will begin with the definition and then consider a slightly more elaborate example. So we say that a deterministic This is important, this idea of determinism, because we will relax that later on. A deterministic finite state machine, or we also say deterministic finite automaton. It depends on whatever text you read. Some authors refer to them as state machines, others as finite automata. So abbreviated, they are using this deterministic finite state machine or deterministic finite just automaton. So these are things that are used interchangeably. Such a finite state machine is, we discussed that last time, a tuple. And I will call this tuple A as in automaton. It consists of 5 elements. The first one is a set sigma. The second one is a set capital S. Then we have something that is called lowercase s naught. We have another Greek letter, a delta, and another capital letter just called F. So, you know, this is a finite automaton. We have something that consists of 5 elements. And this first element, sigma, is a set of input symbols. And traditionally, this set is also called the input alphabet, because one of the very, very important use cases for practical applications of finite state machines are, of course, in computational linguistics and language processing, where these computational paradigms are used to parse text. And in, of course, the case of text, we're talking about alphabet. So I might, you know, again, use the term input symbol or alphabet interchangeably. You have to live with that. And the second element is another set. This is important here. It's a finite set. I'm stressing this finite set of states. This finite here is what gives the whole thing the name finite state machine. So there are just a finite countable number of distinguishable states in such an automaton. This S naught is an element in this set of states, and it is called the initial state. Initial state. And this next thing, this delta, is a function. And it takes 2 arguments and produces an output. And the 2 arguments are first a state and then an input symbol. And given a state and an input symbol, this function delta produces a new state. And it is also called the state transition function. Yeah, and then we do have these, this last element here, and I'll put it here. F is a, I should make that explicit, a subset of the set of states, and it is called the set of final states. And it's quite appropriate that this F now ends up somewhere to the right, because in the context of behavior programming for game agents, we do not really need that. We'll see why. But nevertheless, today we need it anyway. So this is, should probably say it, so I put it in parentheses, I don't know, say for game AI, this is not really needed. Why is it in the context of language processing, parsing? Why would we need that there? Anybody, any idea? So in parsing, you use these automata to check whether a certain, I don't know, whether a string of input symbols conforms with certain grammatical rules. These finite state machines are used to parse Chomsky type 3 languages, regular expressions. You use them whenever you use the term, the command grep on your machine, like to find a word in a text. Then a finite automaton is being compiled, and then the text is pushed through this automaton. And whenever this automaton reaches a state in this set of final states, also called the accepting states, then you know that whatever word you are searching for is actually contained in the text. Right, so there, this is needed. We are interested in behavior programming. We don't really need that. But then again, for what we are going to discuss today, we need it. So let's now look into the example, which is basically the example from last time, slightly extended. Then I have to think about how to make use of this space in the best possible way. So I will begin drawing an automaton on the left-hand side of the whiteboard, and I will therefore split the whiteboard, and all the text will now be on the right-hand side, because we'll need that for our discussion. So let's again look into the example of the behavior of a guard. So we talked about the idea that, in many computer games, you might actually, as a human player, be on a quest for something, I don't know, find a treasure. These treasures are being guarded by guards, and maybe these guards are not human opponents, but computer-controlled characters. So these guards need to show a certain behavior where we would say, okay, this is what guardians do if they have to guard a treasure. So let's look into ways of at least describing the behavior of a guard. So we said that such a guard can be in a couple of states, and let's call the first state just, guard. The second one was called charge. Then we had one that was called attack. Here is a new one, it's called retreat. There is another one called flee. Finally we have die and celebrate. Right? So that is the set of elementary states I say the guardian can be in. And let's begin drawing them. So we have a state called guard, and I'll put circles around these states. Then we have a state called charge. We have attack. We have die. And we have celebrate. And then there is retreat. Retreat and flee. Yeah. So these are elementary situations the guard can be in. And again, remember that I said last time, well, this is a very high-level representation of elementary states. This character, this non-player character, NPC, can be in. And of course, this does not tell us about what it means to guard the treasure, But in computer implementations of these kind of models, each of these states is typically assigned a script of activities to do. For instance, in this state guard, there could be a script that would constantly update the attributes of this game entity called the guard, such that the location of the guard would be increased in some direction, increased, then there probably is a turning point, would turn around, be increased in this direction. You know, so this is the behavior of guarding, going up and down, has to be rendered graphically, has to be, you know, rendered on the screen. These kind of things are done with scripts that are attached to these states. So we have elementary states the guard can be in. And then we talked about how to realize an input alphabet for such a guard. And in our example, it consists of the following symbol, capital H and capital R. Let me immediately clarify the symbols here. So I am using H to indicate a measurement of an attribute of the guard, namely that the health value is larger than 20%, whatever, that this is just a contrived example, right? Again, the guard is a game entity. These entities have attributes like spatial location, health, I don't know, armament, ammunition, whatever you need for whatever kind of game. We can measure these attributes. We can, for instance, look whether this attribute health has a way of, a value of, you know, more than 20% of its maximum, whatever. And if that is the case, I would call it capital H, right? And so when there's a capital H, there's also a lowercase h. That would basically be the opposite case. So if the health is less or equal than 20%, I would refer to that as lowercase h. And this R here, capital R, is used to check or indicate that an opponent is in view, whatever that means. We can compute the distance between the non-player character and our human-controlled game entity, measure their distance, say, okay, if that distance is larger than some threshold, then we call this, it's less than some threshold, then we said, we are now in view of the guard. We can do ray casting, where we can compute whether the opponent is in view. I'll use a lowercase r to indicate that the opponent is in range, which is, you know, basically to say it's now even closer than just in view. It's actually in range of, I don't know, attacking it with the sword, whatever. So we have our first input symbol would be a tuple H and R. The second one would be capital H lowercase r. Then we have lowercase h lowercase r. And then we have a D, capital D, and a lowercase d, where D indicates actually that the opponent is dead. And this D here indicates that the guard is dead. Right. Now, we discussed that sort of extensively last time, that it looks funny to call these things input symbols, right? But they are. They are. When I said sigma is a set of input symbols or an alphabet, I didn't specify how they have to look like. And just because in all the books on computational linguistics and finite state machines, where you typically find examples using zeros and ones as the input symbols, or A's and B's and C's or whatever, nobody would prevent us from, you know, having very complicated input symbols. We can measure these things. We can, you know, concatenate them into, I don't know, tuples. And we could call a tuple with, you know, this particular assignment of the variables could be an input symbol. Who cares? I don't. It's of course cumbersome to write this, so I will switch now to what all the books do, and I will just, in the sequence I have introduced them here, call them A, B, C, well, the last one remains capital D and D. Right? And I'm just doing that because I am too lazy to write H and R and all these things. So I just call this one A, this one B, this one C, and so there you go. Now, the reason why we're doing all of this is that we are interested in implementing a model that would characterize the behavior of a guard. And I just sneaked in that the initial state would be this one here in our example. So what we are interested in actually is this function delta. This is in the context of game AI why we are doing all of this, right? And so bear with me. Now, let's think about what a guard can do. Let's think about this from the point of view of a game designer. And we have already started thinking about this because we said, well, a guard can either guard a treasure, charge, say, towards an opponent that is in view, can attack this opponent, may die after attacking the opponent, may probably win and therefore celebrate the victory, or may retreat or flee. And this should not happen in arbitrary sequences, but that should be triggered by certain events or, say, inputs. So, for instance, if the non-player character is in the current state called guard, and then it would happen that an opponent comes into view, capital R, and the guard has, you know, enough health. In this case, so input is A, as in here, the guard should charge towards the opponent. Maybe draw a sword, stop this routine of going back and forth, but draw the sword and approach the opponent, right? Different script. So yeah, there is a reason for transiting from this state of some certain very elementary behavior, going up and down, to this state, like drawing sword and approaching the opponent. Now if we think about what next, the guard is now in the charge state, could as well happen that now the distance between the non-player character and the human opponent is small enough so that they can actually engage in combat. That is, if in this situation there would be an input of B, the guard would now move to the state of attacking, which would require another script that would realize this attack. Let's see, what could happen now? Yeah, easy case is if the player is well experienced and knows how to fight these non-player characters, it's quite likely that the guard may lose health rather quickly and die, or that can happen. It can also happen that the guard is victorious, and it would mean that, well, you know, after the attack there is need to render a certain victory dance, teabagging, whatever. Yeah, now once you're done celebrating, it's actually reasonable to go back to the guarding state. Right? Opponent is defeated, we have danced, and now we continue walking up and down. Whether that makes sense or not, you know, this is a model of what they do. Would a real life guard do that? Wouldn't they first inform their superiors that they have, I don't know, a body lying in front of their, who knows, right? This is how it's done in computer games. Okay, but of course, what else can happen? What about these two things? Now, I have to be very careful here because this is all about the errors now.
Excuse me?
Yeah.
The transit from celebrate to guard without any input?
Ah, yeah, you know, whatever. It's arbitrary. Okay. It doesn't matter. I don't care about this. Maybe there is several opponents, then we would have probably to go back to attack. I don't know, but you know, this is just an example. Just an example. So say we were in the charging state, so approaching our opponent, and that one would have a long distance weapon such as a bow or a rifle. If they shoot us, we might lose health while actually still charging. So could be that instead of having a lot of health and being in range, we might actually for some reason have lost health while charging, but we were in range of the opponent. So that is to say, basically on input C, we should probably retreat. Go back, like try to avoid a fight. Now, while retreating, it may happen that, I don't know, there is some health package or whatever, something that boosts our health. As when I say our, I'm assuming the role of the NPC. While retreating, we might gain health again and still be in range. So that is basically, we could go back to charging if, while being in this state, the current situation now would correspond to this symbol A here. And, well, if we are retreating and nothing changes about our situation, that is, we are still having low health and low distance, so we then would keep retreating. And if we are in this retreating state and our health has gone up and we are still in fighting distance, then we might actually transit from retreating to attacking. Okay? Let's see what happens if we are in state charge and for whatever crazy reason the opponent dies, maybe falls down some cliff, can happen, who knows. Then we would go back to the guarding state without celebrating because it was not us who sort of was responsible for that death. What else do we have? So if we are charging and not a lot changes about our input, we would still continue charging. Say if we were attacking and situation is still like this one, we would continue attacking. Say if we were in combat with the opponent and our health would drop and we are still close range with the opponent, we should probably stop attacking but go fleeing, right? And if we, I don't know, while fleeing might regain health and are still in fighting distance, we then probably go back to attacking. And if we are fleeing, our health goes back, but we are not in fighting distance anymore, and we probably should charge again. And then finally, if we are fleeing and our situation remains the same, then we should stay in the fleeing state. What else do I need here? Oh, say we are in the state of attacking, and this would be like sort of the opponent would retreat. I probably go back from attacking just to charging. All right, and now, and I don't draw them, I have numerous additional arrows on my sheet here, and they are going from guarding to dying. Basically, there is a transition from every state to dying. It can happen that, you know, some arrows are being fired at the guard and the guard just dies even if it's not in an attacking state. So it might die here, transition to dying, it might die here, it may die here and here. It may not die in the celebration state. This is not counted here, right? In each of these states, the opponent may die, and so there are lots of arrows pointing from here to there, from here to there, whatever. Right? The only one where not the case is here and actually here. So here we see, and this is why people love this, because this picture is this function. This picture is this function. Right? Again, this function delta is a way of deciding the state an agent is in, or should be in, say. So in the game logic, right, typically you have this huge loop where everything has to be done at every cycle. You have to render the game world, you have to update all the game entity attributes, whatever, and make sure that the physics are not violent, all these things. So now, in this game loop, you encounter the subroutine AI, And the first thing that routine does is, in this case, under this paradigm, is to check what is the current state the agent is in, and should it probably transit to another state. Once that is decided, so once the state either remains the same or has been updated, the corresponding script is executed, and then the cycle continues, right? But first thing is, when you enter this subroutine for the game AI, you check what state is the agent in and what state should it be in. Now, again, this is the function delta, right? Because say one of the two input arguments is the state and the other is this symbol, or this sort of symbolic representation of game attributes and their values. We could say, so say we are in state guard. This is the state we are in. And the game entity attributes would correspond to this input value here. Well, then we should transit from guarding to charging, right? And do whatever it means to charge, render the corresponding animations and so on and so forth. Update the attribute that would indicate now the player has drawn the sword and whatever. Again, like if we are in the state of attacking and the game world does not really change, so basically to say we are still in good health and fairly close towards the opponent, then we should continue attacking. Right? Whatever that means, there are some scripts here that would render the animation that would inflict damage to the opponent, that would inflict damage to this character, would cause updates of the game entity attributes, and then in the next cycle we actually might transit from attack to die. Okay, so this delta is as over here. I don't write it down, right? This picture is this function delta. Now I said that in the context of game AI, we are not really interested in this notion of the set of finite states, but for our discussion today, we actually are. So, in this example, the two final states are guard and die. And I will indicate this, as it's usually done in the literature, by putting another circle around them. So these double circled states are the final states. What would that mean here? It basically says, once the game starts and the human player first encounters the situation with the guardian of the treasure, so the game has to create behavior for this guardian. The guardian will start in this initial state guard. And regardless of what ensues, and regardless how long the battle actually takes, and if there's fleeing and retreating and charging and attacking and whatever, you know, this cannot happen randomly because we have fixed how these transitions will happen. But regardless as to what will happen, either this will end in a situation where the human player dies, where the guardian dies. So this is basically like once the guardian reaches that state, you don't have to worry about generating its behavior anymore. Or the human player dies, then we have this victory dance and then go back to guarding. Right? And then the player has to, I don't know, save the last load the last save game and start the level again and probably do better next time. So these are basically the two final states for this guardian. And we need those because in a minute you will have to tell me something about this automaton here. But first, some more remarks as to why these things are so popular. All right, why does the gaming industry love their finite state machines? They are easy to understand. You do not have to be a computer scientist to do this. Right? You can be a storyteller. You can be a graphics designer, whatever. You can be an expert on creating game dynamics without actually having an education in computer science. Everybody understands that. This is really easy. Right? You just sort of think about, no, what is the context? And again, this is rather contextual. This is about the behavior of a non-player character that is basically tied to a certain location, a treasure on some map, just going up and down for all eternity until somebody approaches and then charge, attack, retreat, flee, whatever. It's sort of a very simple behavior. It's totally reactive. There is no reasoning going on here. It will do the same whatever. Right? But it will execute these sort of scripts that render whatever it does in a certain logical sequence. And coming up with these sequences is easy. Everybody can do that. Like, what are the substates of this behavior of guarding a treasure, where guarding also means probably fighting to the death. Right? Everybody can do that. Everybody can draw these diagrams. This is great. Right? Once you have this diagram, you print it out and hand it to the programmers and say, so this is guarding a treasure, we need an implementer. We need a function that does that. So this is great. Everybody can do this conceptually, very simple. In addition, these things are also extremely simple to implement. Does anybody have an idea why?
Generally, scripts for every move is fairly easy.
Yeah, scripts are, somebody has to worry about these scripts, like what has to be rendered, and I don't know, if I am hitting in an attack, like how many points do we have to deduce from the opponent? If I'm being hit, how many, but like if I'm raising my, whatever, like these things, somebody has to worry about that. Can also be done in state machines, right? Like, so in every of these states, there could be either, you know, a list of things to do or another state machine. This, you know, can be hierarchical. Yeah, that's right. That is, you know, we don't worry about this. But apart from that, any idea?
It can be encoded as hash table. Right?
Exactly. Exactly. These things are tables. Right? To realize these behavior transitions, we just have to realize a lookup table. So here we go. I note that. And this is the second reason why they are so popular. That is, in practice, delta is a lookup table. Right? So for instance, we have, I don't know, guard, charge, attack. That is, the columns would correspond to the states the agent can be in. No, the rows would correspond to the states, and the columns would correspond to the possible inputs we, upon designing this behavior, have agreed on. And then, you know, we just have to fill this table. So for instance, if we are in state guard and encounter an input of A, we transit to charge, right? If we are in state guard, where actually do we transit to? If there's a, yeah, if I haven't drawn them, then it's basically a self transition. So if we are in guard and actually there's a B, then here we go to attack. I probably should draw this here, whatever, right? And so on and so forth. I don't even have to, you see that, right? It's a simple lookup table. It's a simple lookup table. So not only are they trivially easy to conceptualize, but they are also very easy to implement. That is, this first thing the AI routine has to do is basically, again, just, you know, check the state we're currently in, is a row, and then sort of determine these input values from the attributes, And then for the given row and the given input value, there will be a state, and then we transit to that state and whatever. That is very, very efficient. Very efficient. So very easy to design and very easy to implement. Now, I need you to look at this and say, wait a minute. Is there something that springs to mind if you look at it? Might be an unfair question because you typically just see this if you do this a lot or whatever. Is there a conceptual difference between retreating and fleeing?
We can have a state where our health is less than 20% and the opponent is still in view. Small h and capital R.
Yeah.
That could lead to flee, actually, in that case.
No, I don't know, like I might have forgotten certain arrows here. Actually, what is this one here? Let me check. I guess that was A. Yeah. So A here. But just have a look at these two states and the delta that would ensue from there. So basically, if we are in state retreat and reader C, we remain in state retreat. If we are in flee and reader C, we remain in flee. If we are in retreat and encounter a B, we go to attack. If we are in flee and encounter a B, we go to attack. We are in retreat, encounter an A, we go to charge. If we are in flee, encounter an A, we go to charge. This is the same. This is the same. Do we need these two things?
Maybe the script is different then.
Yeah, that's a very valid point. And this is indeed why it may make sense. So there are probably two different scripts coming with these two states. But maybe we have not just 7, but 50,000 of these states. And this is more realistic. And our lookup table is more in the area of, I don't know, a couple of thousand rows and a couple of 10,000 columns. And somebody says we need an update of the game. There was a bug in whatever state, so we probably have to introduce another state. So what I'm trying to get at is that even though this is easy, that can be messy. It can be very messy. In particular, if there are many people working on this, now of course in this didactic example I call it retreat and flee, and that already indicates that they are basically the same. But that may not be as obvious as it is here. And sometimes, you're right, they may have a different semantics in the sense that there is a different script executed when we are retreating and a different one when we are fleeing. Retreating could be, I don't know, slowly moving backwards, and fleeing could, drop everything and run. Can be, but maybe we do not want to distinguish these. And this is yet another reason why these things are rather popular, because we can minimize them. Minimizing deterministic finite alternator. I will ever so briefly just touch upon this theory. It's very, very important and extremely well understood because it's so important for the area of, compilers and so on and so forth. But it is well known, there is a theorem that for every DFA, deterministic finite automaton, such as this one, there exists a unique, and this is important, unique minimal DFA. That is, every DFA can either be reduced to something with fewer states, which has the same computational power as the thing with more states, or if it cannot be reduced further than it is already minimal. And there are two kinds of classes of states. Classes of states we may remove or merge. Can be removed or merged. And the first one is the class of unreachable states. Reachable states. If your automaton to realize behavior for an NPC contains unreachable states, there is something seriously flawed. Look into that later on. And the second one is the class of either, one says, non-distinguishable, distinguishable, or equivalent states. And I'll just ever so briefly walk you through this. This is great because the fact that this holds is very much appreciated again in practice, because you can sort of automatically ensure that the machines you have are somewhat as efficient as possible. Right. So, but before we do this, here is some more notation. And I will use the notational conventions typically used in language processing or in computational linguistics. By sigma star, I am referring to the set of all words over sigma. And that's basically to say, I should say all words or strings, probably. Strings, right? We have this alphabet of input symbols, A, B, C, D, and we can create A, B, E, B, B, A, C, 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 whatever. That would be an element of sigma star. Every possible sequence of input symbols is in the set sigma star. So this is a very large set, right? Infinite set. Then there is this notion of epsilon, which is an element, implicit element of the set of input symbols, and that is basically a mathematical convenience to indicate the empty character. And with these two things, we can define the notion of a word, W, and I will write words like this. There is an X colon XS, and so this word is an element in sigma star, and X is a character in our input alphabet, and XS is a sequence of characters. So this basically says we have a word where there is a word XS, like sequence of some characters, and there's one more character in front of it. Right? I use that colon to indicate. This is basically concatenating a character to a string. Now we have this. Then next thing is we generalize. Let me emphasize this. We generalize the transition function. We introduce a new function delta star, and this takes a state as an input and a word, not just a single character, but a word now. Right. We are in a state and we are reading a word, and it transits to another state, and it's defined like this. We say delta star given some state S and a word X, XS. So this is exactly the situation. We're in some state and there is an input string, not just a single character, but a string. This is defined as, well, delta of S and X. This is the delta given by our automaton, the usual delta. If this XS is actually empty, so basically if, you know, delta star of S and X is the same as delta of S and X. Or it is delta star of delta of S and X, comma, XS. So this is a recursive definition as to what it means to process a string. Right? We read the first character of the string, make a transition. In this new state, we read the first character of the string, make a transition until the string does not contain any characters anymore. Right? So this is otherwise. Okay, with this in mind, we can first, ever so briefly, is actually not really important. I'll keep that. First define what it means to be unreachable. State Si is unreachable if there is no word such that we would have Si as the result of delta star as not. So this is, you know, increasing pace here. This says, say we would have an automaton, and we know the notion of the initial state. There is some state we start in, whatever we are doing. And, you know, we process lots of inputs, words, and whatever. And if there is no single word possible such that we would be able to reach this state Si from the initial state, then that state Si is called unreachable. Here is an example. Whatever. So we have the initial state as not, we have a state as 1, a state as 2, and you see I am switching to the usual notation here just for brevity. This has nothing to do with games whatsoever. It's just an example of a state machine. What else do we have? So this is a great state machine, but it's not complete yet because there is another state S3 from which we were to transit to S4 upon reading C. Neither S3 nor S4 are reachable. Right? And this is basically something we have encountered earlier. And note that every state machine is a labeled graph. Ha! Labeled graph. And we have already discussed the notion of connectedness in graphs. So basically, if you're dealing with a state machine that is not connected, you are guaranteed to have unreachable states, but there might as well be, I don't know, something, I'll make it a D here, and this D never occurs. Never occurs, like for whatever reason. Could be, right? And even though this state machine is now connected, it still may be the case that these two states are unreachable. Okay, if you are dealing with a state machine that contains unreachable states, your design is sort of seriously flawed, and you should do something about this. I am not discussing how, but these things can be detected automatically. It is possible to automatically detect if a state is reachable or not. There are algorithms for that. We just ignore them, we just acknowledge that they exist. And then we have that two states, Si and Sj, are equivalent, and we write Si equivalent Sj, if, and here is another sort of very crisp way of writing this down, for every word W in sigma star, we have that delta star of Si and W, if that leads to an accepting state or to a final state, right? If we compute this recursive function delta star starting in state Si with some string W, and that would lead us to an accepting state. And at the same time, if that is equivalent to delta star starting in Sj with the same input W, if that also leads to an accepting state, then these two states are equivalent. Right? And this is exactly the case here. Regardless if we start in retreat or flee, with some string, it will either take us there or there. And yeah. So these are indeed, this is a sort of a stupid example because it will happen for the other states as well. But yeah, you know. But that does not necessarily have to be the case, right? So this example is not sort of general enough, but I have designed it such that we can at least see that it does not matter what kind of input comes in this state, it behaves exactly the same as this state. The difference may be, as she already pointed out, that there might be different scripts attached to the states. So in words like that is to say the machine does exactly the same when either started in Si or Sj. Right? And this example is unfortunately not general enough. But you can immediately see that the machine will do the same when started here or there. It's not as obvious for these two states. And the final thing I want to note is that now we have defined unreachable state and equivalent state, and there are highly efficient, algorithms, and by efficient I mean O n log n, where n is the number of states that can identify these. That can identify these, for instance, and these things are well known for quite some time, goes back to Hopcroft in 1971. There are more other algorithms, not quite as efficient, but lots of algorithms that have been proposed. Well, I'm switching pens because this one is no semantics here, but still it's good to point that out in red. You know, if we say there's an n log n algorithm, then this is fairly perfect. So we can say that the problem of finite state machines minimization is solved. This is very good news for game design. Very good news for game design. Right? Because you know, while designing these games, while designing the behavior of characters using these techniques, that can explode. That can become very, very cumbersome and cluttered, whatever. And then there are algorithms that tell you, oh, this state is actually equivalent to them. Maybe you want to merge them. Maybe you don't because you have different scripts, but this is something that can be detected automatically. So this is great. This is why people love these things. And of course, like let's write it down. So it allows for optimizing behavior models if needed or desired, right? Sometimes you don't want that. Sometimes you don't want that. Okay, let's keep it at that with respect to finite automata. Oh, yeah, wait. It's one more message, and we use the residual to get this message across. So there are scripts associated with each of these states. I should not have erased it already, but anyway. What I have drawn here and partly erased is actually, if you think about it, more than a finite state machine. Right? Because in addition to this function delta that realizes transitions between elementary basic states, we said that in each of these states there is something that is done when in this state. So apparently there is yet another component which I have not formalized. Right? And this is something that baffles me, because finite automata with output, right, this thing actually does something when it is in a state. So it outputs something. It runs a script, and that script renders something and updates attributes and whatever. So it has an output. And state machines with outputs are called transducers. But when you read the game AI literature, it's always called state machine. Always, so they don't make a difference between an automaton and a transducer. But we're at university, so we'll make this distinction, and let's see what a transducer is. So we just note in game AI, most finite state machines are actually transducers. And what is that? We define it. We say that a finite state transducer is a finite state machine with output. So we basically sort of have to extend the model we have been looking at so far, and I shall call it T for transducer. And this is a tuple consisting of a set sigma, a set gamma, a set S, symbol as not, a function delta, and a function omega. And here, this is just an extension of a finite state machine, so therefore this sigma is S, as we had before, just a set of input symbols. S is just a set of states. S naught is an element of S, and it is the initial state. And this delta is still the state transition functions. So these four things are as above. Let's quickly look into the other two. So no big deal. This gamma is another set, is a set of output symbols. And, you know, by the same token, the way we use to sort of map game entity attributes to certain discrete symbols, we can basically argue that scripts attached to states also sort of just produce a couple of symbols, whatever. This is just a general way of thinking about this, right? Of course, in practice, in the context of game AI, these elements of gamma are fairly complex entities because they are scripts, but they are just elements of a set of scripts. So we can, yeah, think about this. Oh, sure, but so for instance, let's can think of an example in game here, but that's just very general. Say you would have a finite automaton that you would use to, I don't know, accept a certain regular expression a b b a, whatever. That's not actually a b b. What is you parse something, and maybe while parsing you actually want to say stuff like this is not a word yet, this is not a word yet, this is a word. So the final states could output, yes, we have found something. Maybe actually could output the location in the string where a word was found that complies with the language. Or you could say, well, let's translate, I don't know, symbols from the Latin alphabet into symbols from the Greek alphabet. So you read A, B, B, and you transduce that to alpha, alpha, beta, beta. They do not have to be the same thing. This is the power of this, right? They can be the same thing. They can be the same thing. But in general, they do not have to be the same thing. And once again, so this is gamma just because it's gamma in basically almost all of the literature. I have discussed the use of Greek symbols with a PhD student of mine from the Far East, and what can I say? So don't worry. If these are just, there is no semantic attached to this letter or to this letter. This is sigma, it's probably for syntax, whatever, but they are just more letters I have in my disposal to indicate things. So I'm just using the gamma to indicate another set. It's a Greek letter. I should probably redesign my script using Latin letters only, whatever. And the same holds for the function omega. This is not a W, it's the Greek letter lowercase omega. This was a Greek letter delta. Why? I don't know. They do it in literature, so do I. This is interesting. We have two possible ways of thinking about ways of producing output. So let me already indicate that. We could say the output depends on the state we are in and the symbol we are encountering. We are reading right now. So given a state and an input symbol, instantiation of attributes, whatever, we don't care, we would produce a symbol in the output set. Or we could say, well, it doesn't matter what we are actually reading, the output only depends on where we are, what state we are right now. Right, so basically just from S to gamma. I have to be careful, this is called a mealy output function, and this is called Moore output. It depends. There are two ways of thinking about what the transducer can do. We now have a finite state machine that does state transitions and usually also does creates outputs. In our case, in the case of game AI, the outputs are once again, say, scripts that are being executed, and we also note that here in this model of a transducer there is no F, no set of final states. Here we don't really need that. All right, there are two more things. We started slightly late, so let's quickly do these two things. There is yet another reason why these things are so popular. They're easy to design, and they are easy to minimize if need be. They're also easy to compose. This is great, and I'm just sort of dropping this DFS. And you see I'm switching between FSM and DFS. It's always the same thing, it doesn't matter. Now it's even probably referring to transducers. I don't really care, I shouldn't say that, but it's really conceptually the same thing here. Thinking about using these things to realize or at least to model behavior, we can also imagine that there is this simple behavior of guarding. You know, this was a finite state machine of 7 states with 7 scripts, whatever. Maybe the guard could also be sent somewhere else as a messenger. Right? So the role of that NPC could switch. Then it could happen that there is another behavior for, you know, being a messenger than being a guard. We can model the behavior of a guard. We can probably model the behavior of a messenger. Maybe at some point there is a transition from, you know, what it would mean to be a guard, being in one of the states of guarding, to the initial state of being a messenger. And whatever, I don't, you know, there's lots of different elementary roles we could think of, and for each of these roles we could come up with an automaton. Now once we have them, we can use them to create more complex behaviors, and this is where it happens that, you know, these things explode. But you can compose them. This is great, because everybody can come up with these easy models and then put them together to more complex ones. So ever so briefly, more complex behavior may be realized by combining simple, let me put that in quotation mark, DFAs. And typically, and I'm really not going into the details here, you can cascade them, and that is to say you have an automaton A1, and there is some transition between one of the states, like and an automaton A2. I don't know, you have this automaton, say the guarding behavior, and I don't know, say after the victory dance, there could be a transition to now go to, I don't know, somewhere report that you just killed an enemy, I don't know, whatever. Right? And that going somewhere could have been modeled separately, and then you just sort of combine these automata like that. Sometimes, and this is now getting a bit more abstract, maybe you want to realize different behaviors upon the same input. That can happen. There would be a switching component here. You know, something is going on, and then you can either do this rather complicated behavior or that rather complicated behavior, but you know, sort of can do several things. Yeah?
Is it then deterministic?
Pardon?
Is it then deterministic?
Yeah, we'll come back to that in a second. Yeah, very good point. That's the last point for today. Her question was, is that still deterministic? No, it is not. But think about the following situation. Let's slightly generalize our example. Instead of a single guard, it could be a team of guards, or it could be, I don't know, a small army of whatever, right? And you would have to have an automaton that models the behavior of an army. In that case, you could sort of have several things in parallel. That you could think of how to execute them in parallel, whatever. The last one is, I'm actually not aware of any situation in game AI feedback. This basically only applies to transducers. It has to produce an output in order to actually work. Behavior does something, changes something, produces some new game state after having been executed, and maybe that game state informs what is to do in the next cycle. But these are just sort of the basic things you can think of as to how to combine or create more complex things out of simple state machines. And now, coming back to your question, and in order to prepare ourselves for things to come, we'll have to relax these things from deterministic to non-deterministic, and we will begin ever so slightly doing this. Ever so slightly. And I'll just define and then I'll discuss it. A non-deterministic finite state machine or finite automaton. They are typically having an n in front of them, so n FSM or n FA. These things, which we are going to define right now, are, or a non-deterministic finite state machine is a finite state machine where the state transition function delta is replaced by capital delta. So this is the Greek letter capital delta. And let's just look at it. So delta takes an input, well, it's basically a pair, again, a state and a symbol. So nothing changes on the input side of the state transition function. But it produces an output in the power set of states. And that is to say, so once again, this power set is the set of all subsets of a set. So we are given the set of states S, and 2 to the S indicates the set of all subsets. It contains S itself, it contains the empty set, it contains, I don't know, sets with just one element, sets with two elements, like all the subsets of S are contained in the power set of S. And that is to say, this transition function now realizes transitions from a state, given a state and a symbol, it may transit to several states. Right? So that is to say that when observing a symbol, say X, in state Si, the machine may transit to one out of several states. And here is an example. So say we are in the state guard and read a symbol A, or the environmental or internal attributes would indicate this situation A, then the character may transit to charge or may actually transit to attack. I don't know. So what it will do is it will transit to one of them, not to both, right? But again, upon the same input, it has different options now. That is the difference between non-deterministic and deterministic finite state machines.
So
Yeah.
If we translate one of them, then the definition, but definition says that it will translate to several. It might translate to several of them.
Yeah. So what this definition says is that it. Okay. This is the set of options, right? But on the input side, we just have S. So basically, we have options, and we have to decide for one of them, and then continue from there. Sorry, I know I can totally see your point, but this is what that means.
Okay.
This is what that means. Right. There is non-determinism here. It's not like so far, you know, given one input, there's just basically one possible sequential state, and here we have several possible sequential states. One of them is chosen, and from there it continues. Right. We will come back to that next week. I can completely see your point. We'll come back to that and relax that even further. Like totally, like really relax that. Not for now. This is just sort of indicating things that are to come. Very interestingly, I should end this lecture with pointing out that one can prove that non-deterministic finite automator are equivalent to deterministic finite automator. This can be done by increasing the set of states in the deterministic automator. So for every sort of subset of states, we would basically replace the S in the deterministic automaton with the 2 to the S, and you can prove that this looks like something utterly different, but in the end it is actually can be reduced to just a deterministic finite automaton. And there, once again, is where this problem of minimizing automata comes into play. Right? These things, this is great. If we accept the fact that we can model transitions like that, then we can probably even more easier accept the fact that we may combine different state machines into larger ones. Right. We will come back to that next week. This Thursday we will talk about fuzzy control. And that's all for today. Are there any questions? I can say by now now you know how games are at least conceptually realized. There are designers who come up with these state machines, and programmers sort of have to fill it with all the details. But this is how, up until today, most video games are realized. Most video game AI is being realized. Great, so then see you on Thursday.